So good evening, everyone. I am Nimesh. I will be presenting a digital interface for short span resistive sensors using SAR technology. This was done by me and my guide Dr. Anoop CS at Indian Institute of Space Science and Technology. There are various types of resistive sensors like thermistors, resistance temperature detector, strain gauge, or giant magnetoresistance. Sensors like thermistor and RTDs have a large dynamic range, whereas sensors like strain gauge and giant magnetoresistance have a low dynamic range or say a short span. We focus on these short span resistive sensors. We digitize the outputs. We are trying to digitize the outputs. There are various existing resistance to digital converters like the resistance, relaxation oscillator based, dual slope based, or direct microcontroller based. And we are trying to. There also there's a SAR based digitizers for resistive sensors available in the literature. This is a block diagram of a SAR based digitizer for a wide span resist. For wide span measurement, suppose if you want to measure from 0 to 5 kilo ohm, then this is ideal. But our work is for a short span sensors. Okay, so there are various merits of SAR-based architecture like high resolution, simple architecture, high speed, and low power consumption. So this has advantages over some of the conventional sources. So conventional sensors like dual slope based. So this is how we designed the proposed digitizer. Is this is a general sensor available in the literature. We have added where RSS here is the unknown source, unknown resistance. Here we have given a input a voltage bias at the non-inverting terminal of an op amp, and we have added some weighted summer and a clean amplifier. The working of this circuit I will explain in further slides. Okay. So we have used additional components of a weighted summer and a clean amplifier. The unknown resistance RSS can be calculated by the equation. The equation is given here. The merits of this scheme are this can be tailored for any short span resistive sensors with known output span, and it requires only a single half bridge configuration for a Wheatstone bridge resistive sensors, minimizing the effects of mismatches of the two nominal resistances. Also, it has an inherent advantages of SAR method. Yeah. So, how this works is there's a DAC which is controlled by a microcontroller which implements the SAR logic. The DAC voltage is given by BR per 2 power n Bn minus 1, Bn minus 2 up to B0, where Bn minus 1 is the most significant bit and B0 is the least significant bit. So what happens is we give a DAC voltage. This voltage is combined with a constant voltage Vp through a weighted summer, and then this passes through the unknown resistance, and we combine this VWS with the negative reference VR voltage, add it, we pass it through a drain, and further we pass the resulting signal through a comparator or a zero crossing detector. Yeah. So how this works is, suppose that our known resistance is RSS. As we determine the bits one by one, first the resistance, the digitizer output will be something like this. Then at the next iteration, it becomes something like this. It comes closer to RSS, the unknown resistance. So after all the bits are determined, our values becomes comes closer to RS. Okay. So in this circuit, RSS is the unknown short span resistive sensor, and this R not RF are known voltages. So the algorithm that is there is, first of all, this DAC has we set the values of DAC using to 0. and then initialize our index I equal to 1, where n stands for I equal to n, where n stands for number of bits in of the tag. We check if I is less than 1, then we terminate the algorithm. Hence, and move to the last step, or we continue. We set the I minus 1 bit to 1, that is the most significant bit to 1. And when the most significant bit is set to 1, we check the values of PC. We check the output of OC. And if this value is greater than 0, we reset the I minus 1 bit to 0, else we leave it as 1. Now we will we update the index, and similarly complete the and this loop repeats. Upon completion of the loop, we can estimate the sensor resistance RSS using this equation. Okay. So now the thing is, so now how does this work? Is suppose delta V is the output voltage of the DAC corresponding to the least significant bit of the DAC. Delta Vs, suppose delta Vs is the residual voltage at the input of OC. So we can, from that equation we can write that delta Vs is G given delta V Rn by RSS. Since delta V is very small, we can approximate this as 0, equal to 0, and hence Vs as the subsequent bits are determined, the Vs comes closer to this value of delta Vs, which is equal to 0 in equation 4, and from there we can back calculate the values of RSS, unknown resistance. Yeah. So now there are some how to choose the parameters like V1, VR, and alpha. Alpha is the ratio of two known resistances used. So our aim is to maximize the span of BWS for a given span of RSS, ensuring that good resolution. We also have to take care of the saturation voltages of the op amps. This is a variation of range of voltage BWS, the weighted summer voltage output with different parameters V1, VR, and alpha. Which we see that the BWS span is around 0.88, when V1 and VR are 4 and alpha equal to 0.2. We selected those, and we saw that for this required BWS is around 11.92 to 12.8 volt, which cannot be provided using the normal DAC. Hence we use the weighted summer. The circuit was simulated using Proteus 8 professional software. And this is the actual value of the resistance, and this is the digitizer output in ohm. We varied the resistance from 4.5 kilo ohm to 5 kilo ohm, and we can see that the digitizer output is linear with varying resistance, and this red color point shows the percentage non-linearity. The maximum non-linearity was around 0.07%. Now the circuit was implemented on the breadboard using two precise decade resistance versus for R0 and RSS. RSS the short span resistance. We varied RSS from 4.5 kilo ohm to 5 kilo ohm. This is the digitizer output versus the actual resistance. Again, and this black color shows the digitizer output, and this red star shows the percentage non-linearity. The output is linear with maximum non-linearity of 0.8%. We also interface this with a GMR sensors. So a GMR sensors has a four terminals. So this is the diagram of the interface. In this, R0 is the one arm of the resistance which is fixed, and RG is the other arm of the resistance which varies with the magnetic field. So these are the components that we have used. This is the signal transduction and flow processor in the hardware model. We have used we have interfaced the GMR sensor with the SAR analog circuit. That circuit, we have used a reference probe and a reference cross meter to measure the magnetic field, and given in external magnetic field was given using the neodymium magnet. This was the experimental setup developed. Uh, this is the digitizer output versus the magnetic field strength. The magnetic field strength was varied from around 1 to 7 millitesla. We can see that the digitizer output is linear with a changing magnetic field, and the red colored stars, direct stars, were the percentage non-linearity. The percentage non-linearity maximum value was 1.1%. With a AA005 GMR sensor. We also performed a repeatability test for this setup. We fixed the magnetic field as 2.9 millitesla and 400 consecutive readings were taken. The standard deviation was 0.747 ohm. The SNR was 76.3 dB and the repeatability error was 1.797%. Here we have compared our works with the some of the with the various digitizing architectures available for GMR sensors. These are the references. Thank you.